In this video, I'll give an overview of how the second exam went for us. So there were two parts on the exam. Each of the questions on the first part were worth 4 points apiece. Each of the questions on the second part were 8 points, and I scored those with partial credit. The class performance on each of the sections, very, very similar, about 70-71% on both parts. If I were to think about exam performance and turn it into a grade, I don't assign a specific grade for the exam, but a lot of times students sort of like this contextual information. So scores a little bit above or below the average would be in the B to B plus range. And then if we look at other bins, both above and below that, we can see scores that would be aligned more clearly as B plus, A minus, and A for the different categories above, and then those that would be somewhat below the average. If we're looking at the specific items on the exam, for the first part, it's a calculation involving gas stoichiometry. So the first task of using PV equals nRT to calculate moles of product, folks had a lot of success with that. Second part, though, we have to apply stoichiometry because it's asking how many moles of the sodium azide reacted. Not how many moles of gas were formed, but how many moles of the sodium azide reacted, so we had to apply stoichiometry for that. Second question was looking at the bond polarity. So I'm thinking about aspects of electronegativity here. We have an ionic compound in the potassium chloride. We have one with two nonmetals in the carbon dioxide. And in between, we have one with a metalloid and then a highly ionic chloride. So I'd put the BCl3 in between the two. A ranking involving lattice energy, I'm first looking at charge, and then I'm looking at distance to break any ties that I have. Folks did really well on this one. The one tie that I see, both NaCl and CSI are both +1 and -1, and so the smaller cation anion leads to a larger lattice energy. Next one, looking at gases. If we want to look at the mole fraction, we could simply see how the number of particles present is proportional to the pressure. So we could look at the 1 atm of O2 relative to the total pressure. That would be one way you could get the mole fraction. You could also take each of these and calculate actual number of moles and then use the mole fraction that way. To determine total number of moles in the container, sort of depends what you did within the first step. This is an application of PV equals nRT. If you want, you could take the total pressure and then use that in this expression, or maybe break it down individually for the first part. Looking at this one, I see this as applying VSEPR theory for 5 different environments. If I look within the first one, I'm thinking about the environment for the nitrogen, and I see that it has 3 bonds and a lone pair. Angle 2 is a carbon with 4 bonds. Angle 3, I see 3 different bonding domains. Number 4, I see the oxygen has 2 bonding domains and 2 lone pairs. And then the final one, I see 2 bonding domains. So if I were to estimate angles on that, I'd say the first one would be a little smaller than a tetrahedral. Second one, very close to our tetrahedral. Third one, a little bit distorted from being 120s all the way across. The angle 4 would be also smaller than a tetrahedral with 2 bonds and 2 lone pairs. And I would predict it would be even smaller than angle 1 because the lone pairs take up more space. And then finally, the carbon with 2 bonds would be 180. So this would be my ranking as I apply VSEPR theory. This is another one where I have to apply VSEPR theory. We initially have Lewis structures. I would describe the first environment as bent. The second one as being square planar. So the first one, this would be similar to a bent molecule like we've seen with H2O that would be polar. And the one on the right, the square planar, would be nonpolar. We'd have the 4 bromine all in the same plane, then a lone pair above and below, making the molecule nonpolar. Applying molecular orbital theory and determining whether the molecular ion is paramagnetic. Paramagnetic, I'm looking for unpaired electrons. So I show the initial stab here if we're looking at N2 or F2 or O2 2 minus that we could think about. So for N2 initially, I see they're all paired up. It would be diamagnetic. But if I add 2 more electrons, they would go into these degenerate pi star molecular orbitals. So N2 2 minus would be paramagnetic. The one on the right here is currently shown for the O2 2 minus. This would be diamagnetic. If we add, it would also be the same number of electrons that I would have for F2. If I add 2 more electrons to make it F2 2 minus, they would go into the same sigma star. So both F2 2 minus and O2 2 minus end up being diamagnetic. So it's only the N2 2 minus that's paramagnetic. Doing a ranking for the rate of diffusion, I'm thinking how the rate is proportional to the square root of the temperature over the mass. So my ranking here is putting the lighter particles, the helium, moving faster than, effusing faster than the slower the N2. I'm also considering how the higher temperatures leading to a faster rate. The one that might lead to some uncertainty would be the combination in between here. You could certainly check it with a calculation by including the temperature and calculating the rate of diffusion. If I did that, I'd be converting my temperature to Kelvin, but that wasn't required. It seemed like most people just came up with this ranking without doing any calculations, which was fine. Looking then at the open response questions for the second part, these were involving initially our topic of ionic bonding. Within this first one, this is getting at the energetics for the formation of an ionic compound. So I'm thinking about how the overall energetics will include the formation of the cation and the anion, and then also the formation of the subsequent lattice. Thinking about the formation of the cation and the anion, it's unfavorable to form sodium plus. Ionization energies are always endothermic. It always takes energy. And it would be very unfavorable to form sodium 2 plus because I'm now removing an electron that is experiencing a higher effective nuclear charge. It's closer to the nucleus. It's in an inner shell. So it would be a lot more energetically unfavorable to remove the second electron from sodium. How about the oxygen? It's favorable to add 1 electron to oxygen. It has a favorable electron affinity for adding 1 electron, but it's unfavorable to form the oxygen 2 minus anion. Adding a negative charge to something that's already negative like an anion is unfavorable. The overall exothermic formation then of the ionic compound is only explained, it has to include consideration of the resulting lattice energy. So if we were to think about sort of our different options, what forms the Na2O has the sodiums being +1 and the oxygen -2. We have the we could think about the lattice energy that accompanies that, how it was unfavorable to form Na plus and oxygen 2 minus, but those would be included with the overall energetics and the formation of the lattice that makes it favorable. If we were to contrast that with NaO, I guess we have the question, if it's NaO, what would be the oxidation numbers within those? If you were to say, okay, I want to do a comparison where it's +1 and -1, in some ways that would be more favorable in terms of actually forming the anion because it's only -1. However, the subsequent lattice energy would be smaller than what you actually see in Na2O. What if you said NaO includes +2 and -2? Well, that would have an even greater lattice energy, but the energetics of forming sodium 2 plus is that much more unfavorable. So it's really this collection of ideas that we have within here. So the answers I was looking for within this were clearly looking at aspects for the overall energetics of the lattice and also a correct analysis of the energetics to form the ions. Within the second one, how the ionic character is less than 100%, it really comes to the question, what makes an ionic bond have some degree of covalency? Why isn't it entirely cation, anion, +1, -1, +2, -2? Are aspects of polarizability? This was Atkins' description for correcting the ionic model. Instead of saying it was entirely cation and anion, what if we had cation, anion, and then the polarizing cation shifting the electron density? This is what makes the ionic character be less than 100%. There was a student that had a really nice analysis, and they included KCl and NiCl as an example, where the electronegativity differences were comparable. But lithium, notice, because it is more polarizing, it's smaller than the potassium cation, it was able to shift the electron density more. And even though the electronegativity were comparable, the ionic character was smaller for the LiCl than the KCl. Key thing I was looking for within this, though, was including this idea of polarizability and how that made an ionic bond have aspects of covalency. This one, most students seem to choose this top portion here, filling in the table. If I were to look at that, I would have two different ions, both of which, as I show within the Lewis structures, resonance is going to be important in each case. If I apply resonance and think about the resulting bond order, I think in nitrite, the one here on the left, the bond order would be 1.5. If I think about nitrate, the one on the right, my bond order would be 4/3. So the NO bond would be smaller in the NO2 minus. If I'm thinking about the bond angles, well, in nitrate, after applying resonance, I'm thinking 120, 120, all the way across, all the way through. If I look over here for the nitrite, it's going to be a bent molecule. I see 3 different electron domains. So if I had to estimate, about 120. I'm less certain because I'm not sure precisely how much the lone pair occupies relative to the other 2 bonding domains. If I'm thinking about a dipole moment, well, in nitrate, they've canceled out. That's something we discussed within class. The bond dipoles have canceled. Over here on the left, because it's a bent molecule, I don't see them canceling the same way. Okay, so I'd say that the nitrite would have a dipole moment. Second part, how is resonance used to account for the distribution of electron density in a polar covalent molecule? Choose a specific molecule. The one that Atkins discussed in this was HCl. And to think about how you could initially think of a perfectly covalent bond in HCl, and then you could have contributions of resonance where you have the different ionic bonds present. You could have a complete transfer to make it H plus and Cl minus, complete transfer to make it H minus Cl plus, but you'd have an unequal contribution of these different resonance structures. The 2 here on the right would be more probable, more likely to occur, and that led to an overall shifting of the electron density towards the more electronegative atom. So that's what it means to use resonance to account for the distribution of the electron density in a polar covalent molecule. Comes back to Atkins' very far-reaching description of how you always have resonance, but the probability of the different structures varies. Here we have a couple applications of valence bond theory. For the first one, we're looking to explain the bonding in H2, C, and F. So within this student's work right here, I saw a description of what the Lewis structure looked like. We had identification for the nature of the hybridization for the carbon and the nitrogen, initial orbital diagrams, and then what took place after hybridization occurred, a description for what contributed to the p orbital, the unhybridized p orbitals contributing to the pi bond. So I thought this was a really comprehensive analysis. For the second one here, where we're beginning to look at aspects of the orientation of the hydrogen atoms within these different molecules, it was helpful to, again, begin with making a sketch for what the Lewis structure looked like, and then either in words or in diagrams, explaining what took place as far as the orientation of the pi bonds within the molecules. So within our first case right here, we would have the unhybridized p orbitals align with each other and keep all of the hydrogens in the same plane. In the second example, the central atom, which is sp hybridized, has 2 leftover unhybridized p orbitals, both with an electron in it. One of them can be used to pair with the partner on the left, but the other one, the remaining one, has to be perpendicular to that and pair with the one on the right. So we find that for the central one, the hydrogen atoms are not in the same plane, but they're perpendicular to each other. And a discussion how if we have 1, 2, 3, 4 carbon atoms, it returns it back into the same plane. This one was looking at aspects of MO theory. Most people answered the second question. An interpretation here for the first one, proposed molecular orbital diagram for NH3. Does the figure itself include hybridization? If I track through, it does not. If I look at the different origin of the molecular orbitals from the atomic orbitals in nitrogen, I see a contribution coming from the 2s, contributions coming from the 2p, but I don't have any molecular orbital formed where it's coming from both an s and a p, so I don't see any hybridization taking place. In the photoelectron spectrum, based on this figure, I see 1, 2, 3 different sets of peaks for the bonding molecular orbitals that would be showing up in the PES data. Looking at the highest occupied molecular orbital, the HOMO, that would be this region right here. This is non-bonding. Notice I have a line coming from the nitrogen side, but nothing from the atomic orbitals on the hydrogen side. So this would be non-bonding. It's coming from the 2p atomic orbitals on the nitrogen, and there's nothing matching up for it with the atomic orbitals for the different hydrogens. That's our description for non-bonding. If we're looking here to think about the lowest unoccupied, that would be the LUMO. Notice that it's combining from the S and then the different S ones on the hydrogen. So I see that the bonding here is taking the S and combining it where the phases match. So this lowest level bonding one, I would say, would be this picture here on the left. The LUMO would be, again, using the s orbital on the nitrogen, but it's anti-bonding. The phases no longer match, so that would be the center one here. This next question, using the this image of showing how we have molecular orbitals formed beginning with the 1s wave functions. This I thought was a question where it worked really well and helped me understand your thinking on it. This was a really strong answer where it points out, let's begin with the wave function that we would have for a p orbital. So with a p orbital, I have 2 different lobes. They could be colored differently, which would designate different phases. So we could look at different combinations. Look at this one right here. So we'd have on the left-hand side, I see it goes down and up. This would be a p orbital for the atom on the left. I see down and then up. This would be a p orbital for the atom on the right. And notice as they come together, this would be describing sigma star anti-bonding with a node in between due to destructive interference in this region. And on the left, this would be when the phases align and I have constructive. Looking at a few different examples, this one, some people went sort of in this direction. So these were trying to make sketches. These were making sketches to show constructive and destructive interference. If we're looking for the ones along the PZ, PZ is referring to our designation for along the internuclear axis. It's forming a sigma molecular orbital. These would be forming off axes are pi and pi star. Here's one where we had a discussion of forming along the Z, where I see bonding and anti-bonding. Or I see a description here of looking at the overall shapes that I could have. And I like this because it's along the Z axis. But again, what I was really looking for was to consider what was the initial wave function itself. So here was another student with, I thought, a really strong description to see how you could have them come together where the phases would match, or come together where the phases did not match and lead to a node in between. So I really appreciated people's contributions on this question. Turning to gases right here, 3 different questions to choose from, and they were pretty evenly distributed across all of them. A description of a Joule-Thomson and thinking about hydrogen gas relative to nitrogen gas. Folks did really well, primarily discussing small attractions in H2 and contrasting that with N2, which would exhibit more real gas behavior. I think responses from this benefited perhaps from seeing this same figure right here, because it was a really, I think, helpful prompt to think about the A and B values present for hydrogen gas. For students that were discussing the compression factor data and making a prediction for C2H2, most folks in a very helpful way made comparisons with CH4 and C2H4. That data was already on here, and considering how C2H2 was similar or different from those, thinking about aspects of size and intermolecular forces and how those played into the resulting data. So the analysis within that question I thought was very well done. For folks that were looking at this first one right here, there was a description of having our gas in our balloon, heating it up, it begins to expand, and how does that influence the rate of diffusion? So almost everybody had a description along the lines of increased temperature that's leading to a higher kinetic energy. Particles are moving around more within the container, more frequent collisions with the wall of the container. So this could lead to a higher rate of diffusion. I really like that analysis, and I think that would be the entire story if this was in a rigid container and I heated up the gas involved. But notice within here, this is with a flexible container. The balloon then is going to expand. The pressure is going to go down as the volume increases. So within here, we have another variable that we have to discuss. So this would be one where, good example of partial credit for people that were talking about this first portion, but then for full credit, going on and analyzing what was taking place now because it was a flexible container and expansion was taking place. What would that do to the rate of diffusion along the way? Looking then finally at our intermolecular forces, most folks answered this first question right here. As shown in this student's shown work, it was really helpful to initially draw a Lewis structure for these. Some students commented how the CH3F would have hydrogen bonding, but we see from the Lewis structure it does not. For hydrogen bonding, we're talking about an intermolecular force acting between molecules where the hydrogen is bound to either nitrogen, oxygen, and fluorine. So even though hydrogen and fluorine are in the same molecule, they're not bonded to each other, so we don't have hydrogen bonding. This student's explanation I thought was really strong because they initially discussed the presence of London dispersion forces that were present for both of the molecules and pointed out how they would actually be greater for the CF4 as that would be more polarizable. But then went on to say, okay, but the data is telling me that there are stronger intermolecular forces in the CH3F. How might I then rationalize that? So the CF4 in a way wins on the London dispersion forces. However, there are additional greater forces that must be present in the CH3F, and those would be dipole-dipole interactions. For the last one, looking at the strength of the attractions as it pertains to the motion, this was a very strong response right here. Thinking about the directionality in a polar molecule, how we have a positive side and a negative side. Thinking how motion then will influence that. What does it mean to think about a distance dependence for a rotating polar molecule? And contrasting that with what would be taking place where rotation wasn't important if we had clear ions or if we had our London forces. So I thought this was a very comprehensive answer, and overall folks did pretty well on this question as well.